I'm going to talk to you about chapter 15.1, Gibbs Free Energy. So delta G, or Gibbs Free Energy, that tells us about the change in energy between two states. And in metabolism, we will use it to look at reaction energy changes. So if we have this generic reaction where A and B combine or react and create products C and D, and we have a reversible process, we have interest in understanding the energy difference between C and D and A and B. And remember from earlier chemistry, we can, for a reversible process, we can write an equilibrium expression where we take the concentration of the products raised to their exponents and divide it by the concentration of reactants raised to their exponents. And this gives us a ratio of products to reactants under equilibrium conditions. When we have a system at equilibrium where there's both a forward and a reverse reaction and those rates are even. Now, Gibbs free energy is a way of looking at the energy difference between products and reactants, and it turns out it is related to KEQ, and I'm going to talk about what delta G means and how it relates to equilibrium. Okay, so if the value of delta G, this is a statement about the energy difference between the left and right sides of these equations. If it's less than 0, that means it's a negative number. We say that it means that the reaction is, or a process is, energetically favorable. Or downhill. That means that it's spontaneous. This reaction will occur without inputs of energy. And in thermodynamics, we call that spontaneous. We also call it exergonic because energy is released in this process. And what that also means is that C and D are more stable than the situation where you have relatively more amounts of A and B. Now, if delta G is equal to 0, then we say the system is at equilibrium. And the energy difference is 0, and the rate of the forward reaction is equal to the rate of the reverse reaction. So you can imagine that if delta G is greater than 0, the opposite of everything from above is true. The reaction is uphill. It's not spontaneous. It requires energy input. And A and B are more stable than C and D under those conditions. Okay, so we often refer to delta G, or free energy, under standard conditions. And if we're referring to standard conditions, we call it delta G naught. So that is the energy difference under standard conditions. And generally in chemistry, that means gases are at 1 atmosphere of pressure, solutes are about 1 molar concentration. Now, there is a relationship between free energy and the concentrations of reactants and products. And so I'm going to define something called Q, which is the same equation as KEQ, but it's just the quotient, means it's the same ratio, but we might not necessarily have equilibrium. We might have conditions that are out of equilibrium. So it's the ratio of the products divided by the reactants. And there's a relationship between this ratio and delta G. So the free energy under any given set of conditions is going to be equal to the free energy delta G under standard conditions plus R times T times the natural log of Q. R is actually the same constant as the gas constant, but in this case it uses the units 8.314 joules per mole degree Kelvin, and Q is that value up above. Okay, so now when we have equilibrium, conditions, delta G is equal to 0. And when we put that in here, 0 is equal to the free energy under standard conditions plus RT times the natural log of Q. And actually under this, if we're at equilibrium, Q is the same thing as KEQ. We can move over, we can isolate the free energy under standard conditions, and what we will get is that it's equal to negative R times T times the natural log of KEQ. Now, in biochemistry, we actually have the conditions that are given for standard conditions in most of chemistry aren't really relevant in biochemistry. So in biochemistry, we have slightly different standard conditions. And when we're talking about that delta G, we call it delta G naught prime. So this is the standard free energy for biochemistry conditions. Okay, so now let's think about systems that are reversible and what that means. And if we go back to our generic reaction that is reversible, indicated by the double arrows, you may remember from Le Chatelier's principle that if you remove C, our system that is reversible that may have been at equilibrium will seek to replace C, and the equilibrium will shift to the right. Likewise, if you add some amount of A, the reaction is going to shift. If you add A, it's going to shift to push the equilibrium towards products. If we remove one of the reactants, like A, then the equilibrium will reestablish itself by trying to replenish it and shift to the left. Now, this is really important when you have many linked reactions. So let's think about a metabolic process with reversible enzymatic reactions. And really, most or almost all enzymatic reactions are considered reversible. They might not be in the conditions at a given moment, but they can be reversible. So let's imagine a metabolic pathway that starts at E and goes through G to H, let's say W, and maybe it ends at X. Let me make this look a little bit better. Okay, so here is our first metabolite. There's the last one in the pathway. Notice how that the product of this reaction, E to G, is now the reactant for the subsequent reaction. G is a reactant that creates product H, and H is a reactant in the reaction that creates product W, and so forth. So you can see that the conditions in one reaction are going to influence conditions of the subsequent reactions in the pathway. And it turns out that in most of metabolism, most of the reactions have delta G that is kind of close to zero. That means that they're easily reversible. Not exactly zero, but close to zero. And so they're easily reversible. And minor changes in conditions in the cell or wherever this is taking place can change flux through, can change the direction of that reaction, whether it's shifting towards products or shifting towards reactants. And you can also imagine, let's say these are all at equilibrium and we add E. Well, if we add E, it's going to push to get rid of it to reestablish equilibrium, and that's going to make G. And then when G's concentration goes up, it's going to push that equilibrium towards H. And so what you wind up having is this set of related reactions that push what we call flux through the entire pathway. And these perturbations of equilibrium that influence the amount of reactions or flux through a pathway, they're controlled at certain points, and these are the regulatory points. And those regulatory points tend to be at the beginning or the end of a pathway. So reactions at entry points and endpoints in metabolism tend to have delta G that is far from zero. Could be a lot less than zero, could be a lot greater than zero. But so these tend to be less reversible. And so they control flux through the entire pathway. So imagine E is our gatekeeper. It's our regulatory, or this reaction, E to G, that is our regulatory reaction. And we create conditions now where this reaction is happening. It's going to increase flux for everything until we get to X and beyond. So these reactions and other entry points tend to control metabolic pathways. And so our regulatory steps tend to have delta Gs that are far away from zero, and it could be in the direction of spontaneity in one direction and not spontaneous in other directions.